Hi guys, this is Dr. Aeronautics. Today I'm going to be showing you a tutorial on how to fly the Delta Glider 4 to Mars. You may have recalled that in the last tutorial I used an extensive array of orbital mechanics equations to fly from Earth to the Moon. This time, instead, I'm going to be using a graphical solution to get there, which makes it much easier on the calculations. Now, of course, we can't get rid of math. You have to keep orbital mechanics in to some degree because we need to know when to depart, and I actually have the time set right now so that departure should be easy. So to start, you take off and get into a circular orbit. We are in a 350 kilometer orbit. It's usually very easy to get into orbit. If you don't know how to do it, you need to watch my tutorial on flying to the moon, which is the previous one, or even just take off and flying into space. Delta Glider 4 tutorial. So now we're going to go to the TransX MFD. And now we select the minus button to escape. Go to the next stage, which is the Sun major body. And now we select Mars. And that angle is good. So we should be able to create a nice trajectory. If you don't know how to figure out the phasing angle, watch my tutorial going to the moon using the orbital mechanics equations. And wow, despite the fact that I was just kind of winging it by guesstimating, I actually got the date really right, which is good. So the next thing we're going to adjust is the outward velocity. This would be, if you had X, Y, Z, and I, J, and K, this would be J or Y, which we're going to start adjusting now. And what we're going to do is we're looking at the closest approach that we're going to have, and we're going to try and get that number as low as we possibly can. So I can tell you now, just about the rest of this is going to be solved with plane change. That's interesting. So, the beginning is just kind of really boring like this. We're trying to get that number as low as we can. There it goes. That's going to be a really long flight, though. There's no way that we can... there ought to be a way that we can get there a little bit faster. No, maybe not. So what is the point? The point is, despite avoiding the math, it's still going to take a long time because it's a complex problem that you have to solve either way. Okay, it bottomed out at 1.6. Okay, we're in the megameters now, and that's close enough. We just need to get into the sphere of influence, and that should bring us in. Yep, it does. Okay. So the next thing we need to do is adjust the periapsis distance to our current radius, which is 6727. 2672. So now I'm going to take control of the craft and turn prograde. So to explain real quick, we're starting from orbit because I'm trying to shorten the length of the tutorial, and I'm only going to be recording during the critical phases of the flight. No cruise phases will be shown. If you would like to see what it looks like cruising between Earth and Mars, check out the XR2 Earth to Mars tutorial. And you notice we have a begin burn time here. So what I'm going to do now is look at the maneuver that we have to do, and I'm going to do a little bit of trig to figure out which direction we need to burn in. So I will come back in a few minutes. Okay, so the burn is coming up soon, and it tells us right here when to start burning. It doesn't, however, tell us the direction. So what I did was an arc cosine equation to determine the direction of burn, and I'm going to take us off the autopilot now. If my calculations are correct, we need to burn 53 degrees outward, and 69 degrees up in the sun's orbit in order for this to work. If this doesn't work, then we can always try it later. And when I say try it later, I meant we can try it in another direction. Actually, if this is the descending node with the sun, then we should probably be burning 69 degrees down. Okay, we'll just start with the first velocity component first, and then work on the other ones. "20 seconds to the start of the burn. "10 seconds. "2, 1, 0, -1, -2. Okay, good. Delta V is counting down. Yeah, it looks like it's going to be down for relative inclination. And no, I got it wrong, it's up. This appears to be making the inclination worse for some reason. So I'm going to pitch down again. And there is a lesson to be learned from all of this. And that is, you need to do the orbital mechanics calculations beforehand. I tried to make it easier on people by avoiding the complex calculations for the trip, but unless you have a graph readout of the unless you have a graphical readout of the direction that you need to burn in, you really need to do the calculations for yourself and then solve them. The good news is we will have one more opportunity to fix our inclination before we get ejected, which is what we want. So now, once the ellipse breaks into a hyperbola, then we can try and fix the burn. Okay. So what do I see? We need to burn up. Hang on. Yeah, we should be able to be burning up. Actually, I'll just worry about that at the inclination. At the node. Okay, now that was a horrid burn, and it was horrible because I didn't do the calculations beforehand, and the TransX that I have right here is actually broken. So now that we've done our ejection burn, we're going to be going higher. We need to turn the filter on to high to stop any excess radiation. The rest of the ship should be in good shape. So now I'm going to fast forward to the node to when it's time to burn again. And then we really need to figure it out. Okay, so we're really close now to the node. Now let's go back and figure out the plane change velocity was minus, which means we're going to be burning down. And that should make sense. And we're going to burn down until the plane rotates into this, which will take a long time and probably use a lot of fuel. Okay, so now we're heading anti-normal, and this is going to be a very long burn, so I'm going to fire up the engines now. Okay, good. This is getting fixed. We're just over 1,500 kilometers in altitude, and looks like we're over India. Okay, so this is stable. Is that the solar inclination? No, it's not. So that must mean this is the target inclination that we've selected. Wait a minute, did that just move? No, it didn't. Okay, so if this doesn't move, that would make sense to me. I don't exactly understand everything on this calculator. But knowing now that this is the inclination, well, that's all I need to know, because then I could, using whether it's a descending or ascending node, I can use the calculations to determine which direction I need to burn in and for how long. Because the problem is I didn't know what this arbitrary inclination was that we were using. But if this is the case, then we just burn until that goes down. Like I said, this is going to be a very long burn, so I'm going to pause the video until we're done. Okay, so I got it down within 10 degrees of accuracy. So unfortunately the nodes are starting to rotate around from me because I was not expecting it to take this long. So very soon I'm going to cut the engines because we'll just be wasting fuel, and then we're going to have to fix the orbit after we've ejected. However, because of the result of the plane change, orbit now looks more like the target orbit that we were expecting. Okay, there's 5 degrees. I'm going to go ahead and cut the engines now. Okay, we're done now. Until we eject. So I'm going to save, and I'm going to stop the video, and we will come back once I have ejected from the Earth. Okay, so it's taken a long time, but we finally exited the sphere of influence of the Earth, and are now gravitationally bound by the Sun. So we can finally fix the problems that are going on. So the way we do this is we turn a maneuver mode on, like that. And then we do the exact same thing. We start messing with the parameters to try and get this to go down. And, well, there we go. It's actually not that far off. So then we adjust, we adjusted prograde. Now we're going to adjust outward. And now this is where we want the numbers to get really small, like around 100 M or smaller. The reason for this is because we want to go straight into a Mars capture. And now we can mess with the plane change and see if that helps us any. And it looks like it will. So it's just about tweaking these 3 numbers until you get the smallest number that you can. So, I'm going to go ahead and pause the video again, and when I find a great transfer, I will return. Okay, so I've got a good orbit that will take me within 285 megameters, probably even closer than that when after you factor in the gravity of Mars. So now the trick with this is this will actually show you a graph of where to point your engines, and this is what I was talking about for engine pointing. In this case, now you don't have to solve the orbital mechanics with arc cosine, because it will automatically tell you where to point the engines. Of course, the scale on here is logarithmic, so it is very difficult to get a 100% pointing accuracy. You'll note that we set the burn up several seconds ago, so it's already expired, but because we're in solar orbit, this time means hardly anything. So now we can go ahead and light our engines and do the final departure burn. Now ideally it would all be done in one burn, but because I was lazy and wanted to make a easier tutorial, which wound up being harder, I wanted to involve less math, which of course your fuel expenditure is directly proportional to the amount inversely proportional to the amount of math that you put into it. No math means infinite fuel. If you put all the math in it you can, then you have the lowest amount of fuel that you possibly can. Okay, so that is the burn. So now what we do is we go back to maneuver, turn maneuver mode off, and look at our new numbers, which is here. And that is the estimated arrival, which will change as we move through space. So now we're pretty much finished until we should only have to do a single mid-course correction right around here, and then we will prepare for Mars entry. See you then. Okay, so here we are in mid-July now, and it's the same process. Maneuver mode on, and then we start changing the numbers again to make better ones. This time we need to get it really close. And when I say really close, I mean like all the way down to Mars's radius. That accurate, because now we are going to want to trim for the arrival with Mars at a specific altitude that we want. Okay, I'm going to pause the video again and come back when we have better numbers. Okay, now this is what I'm talking about, 3.7 megameters. Now if we look at Mars, this should actually put us, yes, that will actually put us on a collision course, which is alright for the time being. So now we switch the view again. And there we have our burn grid, and the burn is going to be orbit plusward. Whoops. Not quite as plusward as I expected. Okay, fire engines. And now I'm going to trim using some translation. Okay.
Rotation.
That's the end of the burn. So now we go back to maneuver mode, turn it off, and it's even better than we expected. Look at that. We're going to go right through the center of Mars. Well, not really, because it's going to perturb. Hopefully that's the last mid-course correction we're going to do. Still going to be about 3 months before we get to Mars, though. So, 7720 means about 120 days. So about 4 months to Mars. So, I'm going to pause the video, and if we have to do one more mid-course correction, we'll do that. Otherwise, I will come back after the... or approaching the encounter. Okay, everyone, the burn was good, and we are now about to start encountering Mars. So there may be one more trim burn just to establish our altitude upon arrival, and then we just coast in, and then instead of aero braking, I'm going to do the full stop Delta V maneuver, because we also have a lot of excess fuel that I'd like to burn off before we land. And here we go. Yes, we are going to crash and burn. But I'm not quite ready yet to do the final trim burn. I want to wait till Mars gets a lot more gravitationally influencing before I do that. Okay, Mars is about to take over, and it has taken over as the strongest gravitational body. So, that's actually really close. So all we have to do is just tap a little bit of... Actually, we're going to be orbiting retrograde if I do this. Okay, so all we should have to do now is... well, this does change a little bit, actually, now. What a nice inclination of about 50 degrees. So,
Translation.
Let's try translating first. This may, yeah, we're gonna need to tap the engines a little bit. Seriously? How am I burning the wrong way? Oh, yeah, wait a minute. No, that's what I want. I am burning the right way. So what I'm doing now is I'm collapsing the orbit and then reestablishing it on the other side of Mars. Okay. Video's taken care of. Okay, here it comes. 500 kilometers below, 300, 200, 100. Okay, now we're positive.
Rotation. Translation.
So now what I need to do is trim this up to a 200-kilometer approach. Done.
Rotation.
Okay, so now we just sit back and wait for the altitude. Oh yeah, and I forgot, this thing already solved the equation, because I was about to do the vis-viva equation to figure out how much velocity we would have to kill, but it's 1469. And let's do a mass calculation. Mass. Okay, 320 kilonewtons of force, 18,807, which means our acceleration is 17 meters per second. So to kill 1469 with 17 meters per second of acceleration means 43 seconds before Paramar is where we begin the deceleration burn to get into orbit. Okay, we're very close to encounter now. Let's play the Mars guessing game. Where are we with respect to Mars? Don't recognize this terrain yet, which probably means we're in the eastern hemisphere of Mars. So our inclination ended up being 23 degrees. I have an opportunity to fix that, and I think I'm going to. So this is an ascending node, and we want to increase the inclination. So we're going to burn orbit plus. Okay, let's start burning. And my inclination is going down. Is this a descending or an ascending node? This is a descending node, of course. How did I get that backwards? The answer means that I must have misread the box. I could have sworn that the hollow box meant descending node. Guess I was wrong. Either way, here's the burn. Whoa. I changed my mind. 50 is kind of high. We'll go with 45 degrees. We could reach 50 degrees, but 5 degrees doesn't make a difference. Actually, check that. We're going retrograde now. Okay, just accelerating a little bit. You'll notice that the periapsis has changed a little bit. I really don't care. I'm going to pause now. I'm sorry, not pause. Disable the autopilot. And fast forward to burn time. Where would this be? "100 seconds to the burn." Actually, not yet. 100 seconds to the burn. Okay, that's about 40 seconds away there. Let's go ahead and face retrograde. We're at such a high velocity that this is almost the orbital speed of the Earth, which is pretty crazy. It's a very high number when you're orbiting something as small as Mars. Okay, 10 seconds from the burn. 5, 4, 3, 2, 1, 0, -1, -2. And we're burning. Oh my gosh, and I just now realized something.
Translation.
So here's the deal. We solved the burn for, the thing solved for the capture delta. It does not include the rest of the orbit that it the rest of the velocity that it takes to get into a circular orbit. Therefore, I should have done the vis-viva, or no, I should have used the number that it got for the periapsis velocity and then subtracted that from the circular orbital velocity. That's a biggie on my part. So when you do the flight yourself, make sure that you know how to, or rather remember to do this, because it is very important. Okay, we're captured. And I'm going to have to restart the video. Now that we're captured, we no longer need this screen. Okay, I have a sufficiently low enough orbit now. I'm going to go ahead and cut the turbo pump. Okay, well that's actually not that bad. So I'm not going to target landing at the base. Instead, we'll just land at some random place. By the way, I was right about the eastern hemisphere of Mars, because this is Olympus Mons right here. So I was correct on that department. And, well, I was using the ecliptic frame, stupid of me. So instead of 50 degrees, we have a steep 70-degree inclination. Even better. Which means we technically wasted fuel. But, that's the price you pay if you don't want to do the math. Wait for us to go around the back. Okay, time for a little circularization. Okay, that's done. Okay, so now we wait to go around the back side of Mars. That didn't sound right. Let's see if the auto land feature can work for Mars without a runway. Because if we can give it, if we can tell it where to land, then that would be kind of nice. Maybe we don't have a, looks like we actually don't have a, landing autopilot. I thought we did. I guess that means that we're going to have to manually land, and maybe I'm thinking of the Aero Freighter that has the, landing autopilot. Okay, so here's dawn. And we're going to perform our deorbit here. So we're going to open the retros and fire away. Okay, that's plenty good as far as I'm concerned. Re-entry angle of 2 degrees should be fine. Okay, now we sit and wait. Again.
Rotation.
We're going to want to start watching that dynamic pressure. If it starts coming up earlier than I'm expecting, then we'll have to close some stuff. I'm not going to begin preparing for re-entry until 160 kilometers. As I recall, the scale height of Mars should correspond with that altitude is where we want to start preparing for re-entry. So we're going to land in the lava flows southwest of Olympus Mons in the southern hemisphere. Okay, looks good. So yeah, we should be ready at 160, like I was expecting. Okay, it's time to get ready for re-entry. So this is going to be our version of EDL. So something that I've been doing off screen, but I forgot to explain what I've been doing. You need to keep an eye on your oxygen supplies. We still have plenty of oxygen on board, but you notice that we did run through the tank. If we didn't have that much O2, then we would have to be concerned about that. Checklist 5, re-entry and deorbiting. Nose cone is closed, airlock doors are closed, seatbelt on. Put the controls to atmospheric auto because Mars has an atmosphere, in case you didn't know. Main and backup systems on. Stow the radiator. I'm not ready to reduce this to medium yet because we're still very high. And Mars doesn't have a thick enough atmosphere to really protect. Close the retro door here. And the radiator's retracted, so that should be it now. Oh my gosh, I almost forgot about the antenna. I actually didn't use it this time at all, but nonetheless we're going to store it. Alright, so that's the end of the checklist. Forget the strobe. I don't know why you need a light. I'm at Mars. Okay? It's not like we're going to crash into some other airplane. Alright, so see you at re-entry interface. Okay. Now you should know by now that in Mars I prefer to use the blue HUD because it obviously blends in. Let's go ahead and turn this to vessel mass, the second page, so that we can start seeing this re-entry information. 17,355 is good. As I told you before, the code is set so that if you weigh over 19 tons and you touch, no matter how lightly you touch, I've tested this, you could land at 0.1 centimeters per second and you will magically explode as if something happened. Same thing with landing. This is where it's going to come into play. You will note that at the vessel limitation chart, the maximum landing speed is 200 meters per second. You break that by 1 meter per second, your craft will magically explode. Just one. So you have to remember that. Now, our wings are not big enough that we can actually land below 200 meters per second on Mars. So, just like Curiosity, we have a really weird EDL. It's basically where we go in as an airplane, and then all of a sudden we start activating retro thrust and slow down before landing like a hover jet. Just like the spacecraft in Star Wars, actually, now that I think about it. And it's time to get ready for re-entry. 2 degrees on Mars? You need to get to know the Martian atmosphere program. Okay, that's the manual re-entry. Good.
Re-entry autopilot engaged. Please check vessel state.
I don't care about the strobe. Now, Mars is actually quite dense, so we're going to start with a very high angle of, well, not very high, but a high angle of 55 degrees. Yeah, so it gets angry because our re-entry angle is greater than 2 degrees, but frankly, I think we could still enter at like 20 degrees and still be fine. Let's see how long this mission has been. This mission so far has taken 191,648 seconds. Or in other words, 133 days? Seriously? There's no way that's right. Yeah, 133 days. Huh. Thought I'd be much longer than that. No, there's no way that's right. It takes 8 months from the calculation. Anyway, we need to pay attention now because we're re-entering. Which means I need to keep an eye on the temps and the G-forces. Nothing should get too difficult, though, because this is Mars, which means things are easier for some time, and then when it comes to landing, it's difficult. Why is the maximum G-load 2.2? Oh, maybe that's the maximum that we've pulled so far. Yeah, that's probably a maximum. Then I wonder how you reset that. If maybe that gets reset upon landing, or you press this and it resets, or there's a different reset button down here. So we're not going to arm the ejection seats because the Martian atmosphere is too thin for parachutes. I'm even surprised why they've even given us ejection seats, because unless you're on Earth, it works. If you're on Mars, okay, Titan. If you're on Titan, it'll work. If you're on Venus, it'll work for some time, and then you'll die. Okay, re-entry interface, I believe, is around 50 kilometers on Mars. So we're really close. Meanwhile, I've noticed that the space is starting to look a little bit orange, which means that we're going down through the layers now. And very soon we should start hearing the hum of the atmosphere. Okay, 50 kilometers. And yep, I would just about call this interface. Dynamic pressures will be high in almost no time. Okay, we're slowing down at a considerable rate now, so you can see our orbit is now decaying quite a bit. And here we go, -2 meters per second. and our dynamic pressures are above 1 kilopascal. It really is crazy how thin Mars's atmosphere is, despite how bright it is. On Earth, if it had this kind of a light absorption coefficient, or if it had Earth's light absorption coefficient, then you wouldn't see an atmosphere, because the Earth has a very clear atmosphere. The nose cone temperature is now above freezing. Except this is Mars, so that's different. But still, 0 degrees Celsius is considerable, because it means the nose cone temperature is now warm. Just under 100,000 feet in altitude now. Okay, now I'm starting to hear the atmosphere. Acceleration has now reached 1g. So on Mars, the stars seem to disappear at about 70,000 feet, which is kind of funny because that's about where they disappear on the Earth. Go figure. Okay, 1.5 Gs. I'm going to start shallowing our re-entry angle at this point. Okay, it looks like our G-forces are topping off now, so yes, the temperatures are going back down. So we're almost finished with re-entry already. We're now below, just getting below 30,000 feet. What? Oh, okay. That's what I wanted to do. Gonna start shallowing out the angle now, because we're coming down pretty fast. We're actually coming down really fast.
You are cleared to land.
Okay, we got it. Angle of attack has come down. We're now in atmospheric flight in Mars, and you'll notice that it is not quite thick enough to allow for forget it. We'll just do something else. You'll notice that it's actually not... What was I saying?
2,500.
It's not a high enough pressure to switch off of the RCS yet. Now you gotta watch the slope in Mars, because the it takes a long time to turn the air flight control surfaces. At 1,000 meters, I'm going to turn on the atmospheric hold autopilot. Okay. Right, how do I turn this on again? Pro 400, spec 25. Nope. Gotta be fast. Shoot. Gonna have to do it manually then. Being picky, stupid thing. Okay. Time to figure out an autopilot to hold the altitude. Ugh, come on. Atmospheric autopilots in this thing suck. Pro 110, spec 0.
Atmospheric autopilot engaged.
There we go. Got it. That's what I wanted. Okay, so now the next thing that I need to do is go to the vessel limitation chart and figure out what the maximum pressures are that I can open the doors at. One kilopascal for every door except. Are you telling me you didn't include the maximum pressure for the hover and retro doors? No, you didn't. What the heck? Well, I'm gonna have to save and try and open it. Now, why are we tilted like this? What kind of an atmospheric hold is this? Oh, that's why. Wait a minute. For 2 and 8 for 7 and 9 for. Ah, there we go. Okay, this should help fix it. Okay, well, there's nothing to do, so... Okay, we didn't explode. Good. Now I have to find the autopilot for... Horizon level, Pro 200, spec 5.
Atmospheric auto.
Stop doing that. I hate when you cancel a program, it shuts the engines off. Okay, this is the point now where I start adding hover thrust. Okay, now I'm going to cut the engines. And this is where the weird landing profile starts. And here comes the deceleration.
500. 400. 300.
You'll notice that it takes a long time to slow down in Mars, so I'm going to pause the video and come back when we've slowed down. Okay, so we've nearly reached the point now where we can land safely. So I'm going to begin moving towards the ground. And I didn't notice, but we're actually really close to the poles. We're at 70 degrees south. So this is really close to the poles on Mars, and judging by how high the sun is, this is southern hemisphere summer. Okay, I've now cut the main engine. 60 meters per second is plenty slow enough to land.
100.
And putting the gear down. Whoops! No hydraulic pressure. That could be a huge problem.
Gear down.
Gear going down. Let's give our last checks. We're under 200. And we're under 19,000. So we're
50.
ready for landing.
40. 30. 20. 10.
'Okay, that's touchdown. Autopilot off, brakes on. Okay, we've now stopped. Welcome to Mars in the Delta Glider 4. It was difficult to get here, but we got here nonetheless. So, this is why I say the Delta Glider 4 is so much better for flight outside of the atmospheres. Because with the XR2 Raven Star, you have the scramjets, and you can land a lot faster than you can land in this craft. So there's a lot of conservation in terms of that point. So now we can close the retro doors and the hover doors. And, well, we can move the Windows filter back to medium. And we still have plenty of oxygen. So that's how you get to Mars in the Delta Glider 4. I think this tutorial was longer than I thought, but I think I'm going to have to revert the length of the tutorials because I just can't do them quickly. It's just really difficult for me to do them quickly, just because of the way I do things. So again, welcome to Mars, and I will see you guys next time for the perfect landing tutorial. See you next time. Bye.